So this is something that's just a visual representation of what's going on with the mean, median, and mode, and how certain types of graphs and skews will impact that. Okay, so typically what we see when we have like a bell-shaped curve, when the data is spread out, the mean, median, mode will line right up in the center. Okay, the mean is always the center. Okay, in all of these. This one is a right skewed, and so when the mean is in the center, that means these values up here are quite a bit larger than these over here, but more of the data is to the left of the mean. So when something is positively skewed or right skewed, the data is pulled to the left of the mean, which means the mean is higher than the median, and oftentimes the mode in this particular case. If we have a negatively skewed or a left skewed distribution, again, the mean's still in the center, that means it's pulled to the right and more data exists up here, and so now the mean is the smallest value between the three measures of central tendency that we talked about in 3.1. That's something I just wanted to go back to. I forgot to hit on that yesterday, and want to make sure that you're clear on that, because that's something you're going to need to know.
For the quiz?
Yep. Okay, all right. Let's get to the rest of 3.2. So in 3.2 we have something that's called the coefficient of variation. And what the coefficient of variation allows us to do is to compare how spread out data is even when the data is really not related to one another. Okay. And so what this is, it's called we'll compare the standard deviation for lists that consists of different variables. The coefficient of variation allows us to determine how variable, how spread out data is, even when, like yesterday's example, we had brand A and brand B, so we assumed that we were talking about the same product. We can find and compare the spread of data even when the data is unrelated to each other. Okay, and that's really what's going on for the coefficient of variation. To find the coefficient of variation is fairly simple. All right. Again, first of all, it's expressed as a percent. So make sure when you find the coefficient of variation that you convert it to percent. There is a sample formula and a population formula, and I'm going to show you both. But the reality is what you do to find the coefficient of variation is the same thing, whether you're talking about a sample or you're talking about the population. And it looks like this. All that's being said here is we're going to take the standard deviation and divide it by the mean. That's all the formula is. On the left side, you've got the sample standard deviation divided by the sample mean. On the right, you have the population standard deviation divided by the population mean. At the end of the day, it's standard deviation divided by mean. That's how you find the coefficient of variation. And this helps us decide which set of data is more variable, meaning which set of data is more spread out from the mean compared to each other. Okay. Here's an example. The type of thing that you're going to need to know how to do. You can take a picture of that if you wish. So here's what's going on. We're comparing sales of cars to commissions. Do you guys know what commissions are?
Yeah.
What is a commission? Percent of the sale, right? So people who work on commission, a big part of their money that they earn is made off of the number of sales and the amount of sales that they make. So in this case, we're comparing number of sales to commissions. All right, those variables are really, I mean, they have a relationship, but the set of data for the car sales and the set of data for the commissions really are two totally different types of numbers. Okay, so when we ask to compare the variations, what we're asking for is to see which set of data is more spread out, or which set of data is bunched more closely together. Okay, since that's what 3.2 is all about. So they give us the standard deviation and the mean for both car sales and for commissions. So go ahead and use that formula that I showed you to find the coefficient of variation for the car sales and find the coefficient of variation for the commissions, and then decide which one is more spread out or more variable. Go. Remember that your final answer should be represented as a percent. It's pretty straightforward. So that's your setup. That's what you should have had. How many had that? Okay, so my car sales, number of sales, the standard deviation is 5. The mean is 87. For commissions, the standard deviation is 773. And the mean is 5,225. So when I convert those decimals and then to percent, the coefficient of variation for sales is 5.7%. For commissions is 14.8%. Okay? Here's what this means. It means since the commission percentage is higher, that the data for commissions is more spread out. And the way that we say that is this. We say that the commissions are more variable than sales. You could say sales are less variable than commissions. That would be another way, perfectly good way to express it. But that's what this really means. The numbers involved with sales and the numbers involved with commissions can't really be compared on their own. However, the variability of that set of data can be compared using that coefficient of variation. Okay? So again, the coefficient of variation allows us to compare two separate sets of data, unrelated sets of data most of the time, in terms of its variability, variance, its spread. Okay? That's what the coefficient of variation is good for. All right, the next part of this section is what's called Chebyshev's theorem. Yes, Chebyshev's theorem. Chebyshev's. So I want you to write this down. Yes, write it down. As we're about to find out, the number of standard deviations away from the mean is going to be a concept that we're going to talk about over and over again. And Chebyshev's theorem helps us figure out how much of the data lies within so many standard deviations of the mean. That helps give us an idea how bunched up the data is or how spread out the data is. Okay? And so what we do is we use this formula, 1 minus 1 over k squared, to find the minimum percentage of the data that lies within so many standard deviations. Okay? And that's what k stands for. In any given problem, the data can be within so many standard deviations. A couple things that you need to know about k. It has to be greater than 1. If this was equal to 1, this all equals 0 and we have a problem. So k has to be greater than 1 for this to work. K does not necessarily have to be an integer. A lot of the time k is going to be an integer, but not always. And what this ends up giving us is a percentage. Okay, it says proportion, but we're going to think about it as a percentage of the data that lies within the so many standard deviations. In this case, within k standard deviations. Okay. Now, the values that you were finding yesterday that was coming up with the standard deviation was how far away each standard deviation was from the mean. Okay? And again, that talks about spread. So let's look at some examples and how to work through this a little bit so it makes a little more sense to you. Okay? One of the things you need to understand is at least 75% of all the data in any given set will be in between two standard deviations of the mean. And the reason that I know this is because we're saying k equals 2. If I plug this into Chebyshev's theorem, okay, this is 1 minus 1/4, which is 3/4 or 75%. So within two standard deviations, at least 75% of all the data, which means there could be 25% of the data outside of 2 standard deviations. And this is gonna, at the end, I'm gonna show you a nice little graph that I think is gonna help make it make a little more sense. Okay, additionally, for 3 standard deviations, at least 88.9% of the data is gonna be in there. The only thing different between what's up top and what's down below is the value of K. Okay, so once we get to 3 standard deviations away from the mean, we've got most of the data encapsulated in that area.
Is that how the questions will be worded on
We're gonna go through some examples.
the, okay.
Let's go through this a little bit and break it down with some examples, okay? Let's say we have a set of data where the mean is 65 and the standard deviation is 7. Okay? These are some of the problems that you worked on yesterday. We found the mean, we plugged that all in the calculator and found the standard deviation. Okay? Here's what this means. Okay? 2 standard deviations above 65 is 79. Okay? And the reason that that's true is since 1 standard deviation is 7, 2 standard deviations is 14. So I'm moving away from the mean. So 1 standard deviation is 7 away from the mean. In either direction. I could be 1 positive standard deviation away from 65. I could be 1 negative standard deviation away. Okay? But we usually say below the mean or above the mean. Alright, 2 standard deviations. Since 1 standard deviation is 7, 2 is 14, which means at least 75% of the data for this particular set, okay, is going to fall between 79 and what's the lower end? What's 2 standard deviations below 65? 51. So 14 below or 14 above. So 2 standard deviations below 65 is 51. So what this means is that between 51 and 79, we expect there to be 75% of the data, at least 75% of all the data. So at least 75% of all the data in the given data set is going to fall between 51 and 79. Why is that important? Well, that means most of the data, 3/4 of the data, if not more, is going to be in between 51 and 79. So when we talk about analysis and trying to decide what's happening in a data set, I can tell you that most of the data is bunched in between 51 and 79. That gives me some insight to draw conclusions. And ultimately, that's what statistics are all about. You're trying to do some analysis and draw a conclusion about something rather than just having a bunch of numbers. All right? There are questions on that. If we ask for 3 standard deviations, so now I move further away from the mean. In this case, 3 standard deviations would be 21. So I'd tack another 7 onto 79, that's 86. Take another 7 away from 51, that's 44. So now 89% or 88.9% of the data is now encapsulated in that range from 44 to 86. Okay. All right, so here's a visual representation of what it kind of looks like. So if I had some distribution and I wanted to look at it in terms of Chebyshev's theorem, it makes sense when we look at it visually that 75% of the data is going to be in there because most of it on the outside isn't there. Right? So let me throw this out there. If it was exactly 75%, how much is this region? How much percent of the data is over here? 12.5. How'd you come up with that? There's 25 left, so each side here and here has to be 25. So half of that's going to be 12.5. And I could draw those lines there for 3 standard deviations with the 88.89%. But hopefully you get the gist. All right, here's a problem, a similar problem that you're going to need to do in your homework. Okay, if you want to write this, you want to take a picture, I don't care. But get that in there and we're going to work through this. Here's the situation, okay? Survey local companies found the mean travel allowance for executives was 1/4 per mile. That's pretty low these days, just FYI. Standard deviation is 2 cents. Okay, we want to find the minimum percentage of data that's going to fall between 20 and 30 cents. Okay? So we understand, one of the things that we have to understand is that the mean, that 25 cents, has to fall right in between 20 and 30 cents. So that range that we came up with on the previous problem, where the standard deviation was 7, we went 14 above, 14 below. The difference between this problem is we don't know how many standard deviations away from a quarter 30 cents is. We don't know how many standard deviations away from a quarter 20 cents is. And we need to figure that out. Okay? That's what we have to do first. Once we know how many standard deviations away from the mean 30 cents is, or 20 cents is, then I know my K value. And once I have my K value, you plug it in the formula and figure it out. Okay? So, here's how this is going to go. I know that, and I chose the upper value. The upper value in this case is 30 cents. I know that there's 5 cents between a quarter and 30 cents, right? If you wanted to go between 20 cents and a quarter, it's still 5 cents, if you want on the low end. All we're trying to figure out is the number of standard deviations. The key thing that we need to figure out is how many standard deviations away from the mean is 5 cents. Okay? So how would I do that? Divide 0.05 or 5 cents divided by the number of standard deviations. I'm sorry, the amount of a standard deviation. So I need to know how many standard deviations are in 0.05, and all I have to do is divide it by 0.2. Okay? So when you go to work through these problems, you first have to figure out how far away the upper bound or the lower bound is from the mean, and then you have to divide that by what the standard deviation is to determine how many standard deviations away from the mean you are. Okay? And this is 2.5, 2.5. So that's why when I gave you the original formula, K, we said it doesn't have to be an integer. Okay, 5 cents is 2.5 standard deviations. 30 cents is 2.5 standard deviations away from 25 cents. 20 cents is 2.5 standard deviations below 25 cents. So now we have K, which means now we can find the minimum percentage of data values. So plug 2.5 in to Chebyshev's theorem, and you can figure it out. Because what this is telling you is K equals 2.5. So plug that in the theorem, change it to a percent, see what you get. Okay, so I plug it in the formula, you get 84%. So that what this means is, so we've answered the question. Okay, 84%, the minimum percentage of data between 20 and 30% is 84. So at least 84% of all the data in this data set falls between 20 and 30 cents. It's possible that there's more, but a minimum is that it's going to be a minimum of 84%. Okay? So in this type of problem, you have two things. One, instead of them giving you this number of standard deviations away, you have to find it. And then two, plug it in to find the percentage. Okay? Questions on that? All right, next thing. We're almost there. Regardless of the shape of the distribution, Chebyshev's theorem works. Okay, if it's a positive skew, if it's a negative skew, if it's a bell curve, okay, could be uniform, whatever, it's going to work. And the key reason why it works is because they say a minimum number of values. If they said the exact number of values, it would be different. Okay? That being said, when the shape is perfectly bell-shaped or a normal curve, and we're going to talk about normal curve and normal distributions later on in the year, that makes up the empirical rule. So if you hear talk of the empirical rule, they're telling you that the distribution is a perfect bell-shaped curve. And when we have that situation, okay, when we have that situation, we have a better idea of how much data is in between one standard deviation. We have a better idea of how much data is in between 2 standard deviations and in between 3 standard deviations. So the numbers change. Okay? Now, we couldn't use one standard deviation with Chebyshev's theorem. Okay? We couldn't use it because one's not allowed. Okay? When we said two standard deviations, okay, we were at least 75% of the data. However, in the empirical rule with a perfectly bell-shaped distribution, 95% of the data is going to be within two standard deviations. That's different from Chebyshev's theorem. And it has to do with how the distribution, how spread out the numbers are. Okay? And in this case, instead of saying at least 75%, we're saying it's approximately 95%. So it's quite a bit more than 75%. And quite a bit more than 88.89% for three standard deviations. And I'm going to show you a bell curve and how it really looks. I'm going to show you a distribution, and then I'm going to show you a bell curve. And those are things you're going to want to make sure you've got a good sense of what's going on. Okay? I'll let you catch up, and then we'll show you those two things. Here's what we're talking about for a perfectly bell-shaped distribution. Okay? And notice here, we have the mean right here in the center. Okay? This means plus one standard deviation, plus two standard deviations, plus three standard deviations. And this is below. Okay?
Is that model not in our book?
I'm sure it's in your book. I don't know what page though. The next one is not in your book. Okay? So, in other words, right here, in between one standard deviation plus or minus, 68% of the data will exist. In the empirical rule, when the data is perfectly bell-shaped. Okay? Two standard deviations for Chebyshev's theorem, we said at least 75%. For a perfectly bell-shaped curve, 95% of the data is going to fall in there. And of course, when we get outside to three standard deviations, 99.7% of the data is going to be there. Okay. Here's what, when I say bell curve, here's what we're talking about. Okay, and this is not in your book. But notice the distribution. Okay, instead of putting the arrows on top on the outside, for this bell-shaped curve, the arrows go on the inside. So I get to see a better look at where the data, how much of the data falls inside there. And then I get to see how much of the data falls inside these two standard deviations. And then lastly, those three. Okay?